Okay. Bismillahirrahmanirrahim. Good morning, everyone. Can you hear me?
Yes, sir.
Thank you. So we continue our lecture for this second week. Slide number 40. Okay. The root locus procedure. So in order to construct root locus on S-plane with the imaginary axis versus real axis, we need to follow several rules. And these rules is about 10 to 11 rules, okay?
Know earlier that you cannot attend the class. All right, and you need to.
So first, we know how to sketch, okay, by freehand draw. And this plot can be refined by this root locus procedure rules, okay? By first, we mark the open loop poles and closed loop zeros on the S-plane, okay? And then we follow the rules, okay? Start with rule number one, number of branches, okay? So number of branches is equal to the number of open loop poles, okay? So if the open loop poles has 3 open loop poles, therefore the root locus have 3 paths, okay? 3 open loop poles, so consequence, we have a 3 root locus paths. Rule number 2 is symmetrical. So the root locus is symmetry about the real axis, as I shown you in the previous example. Okay. Where you have a real axis, imaginary axis, and we have open loop poles at 0 and -10 in the previous example. Okay. So two open loop poles will consequence two root locus paths, which is start from -10. Okay. Let us go up towards infinity. And then the second one is start from 0 and then ended at infinity as well. So the meaning of symmetrical, if we flip this S-plane on the real axis path, okay, we flip, kita lipat lah, we flip this S-plane, so this blue line and the green line will touch together, okay, after the symmetrical flip, okay. So that is the meaning of symmetrical on the real axis. And then rule number 3 is the real axis segment, okay. On the real axis, for k greater than 0, the root locus exists to the left of odd number of real axis. Finite open loop poles and or zeros. Okay. So imagine we have these examples, okay, to realize what is rule 1, rule 2, and rule 3. So this is the transfer function that I mentioned just now, where R is the input and CS is the output. Okay. So K is the gain that varies along the line of root locus. So this is the open loop poles -10, open loop poles at 0, and -5 is the break point. Okay. So we have two branch. One is on here, and the other one is on here. So two locus path due to the two open poles, and it is symmetrical about the real axis when you flip on the real axis. For rule number 3, if you have a open loop transfer function as shown here, okay, And this is a unity feedback where h is equal to 1. So we have two open loop zeros, okay, which is -3 and -4, and two open loop poles where is a -1 and -2, okay. So we plot on the S-plane, okay, imaginary versus real, and we found that there is a locus on the real axis. For example, this one, okay. You can see that there is a root locus on the real axis for k greater than 0, okay, to the left of -1 and -3. And if we plot this open loop transfer function, the root locus is shown here, okay, where you have two paths. One is start from -1, -2, -3, and -4. Starts from here and then ended here, okay. And we have two breakpoint. This one is a breakaway point, and this one is the break-in point. Okay, one is away, one is in. The difference is you can see that the breakaway point is between two poles. Okay, while the break-in point is between two zeros. Okay. And of course, the going out and going in directions of the arrow. Okay. Rule number 4 is the starting and ending point. So as I
Sorry, sir.
yeah,
Sorry to interrupt.
yeah,
I think you already went through this Monday.
really.
Yeah.
Oh,
I also checked with the recording. We already
okay,
until rule
okay. So where do we stop?
page 59.
59. Eh? Sorry about that. Okay, go to slide 59. Maybe I'm getting confused with the other sections. Okay, 59. This one is it?
We should enter rule 7 now.
Rule 7. Okay, rule 7.
Yes.
I'm sorry. Thank you, Lim. You need to remind me because kita nak raya ni dah tak fokus lagi agak ni. Okay, sorry about that. So rule number 7, we already done rule 1 until rule 6, and then we go to the rule number 7, where the rule number 7 is the intersections between the rule locus and the imaginary axis. The blue line is the root locus, and this one is the imaginary axis. Okay. And our point of concern is here. Okay. The crossing, or we call it as the intersections. Okay. So this intersection is vital because it is a point where the root locus separate between the stable, unstable, and the marginal stable. For example, okay, this is the real axis, omega axis. As I told you before, this region is stable. Okay, this region is unstable. And along this line of the imaginary axis is critical. Okay, or we call it as a marginal. Okay, so this is the basic concept of the stability. Okay, so back to the locus. So this point is vital due to the fact that it will split between two regions. Okay, and in order to find this point, we have to use Ruth-Lewis criteria. Ruth-Lewis criteria you already learned in the modeling and the previous semester module, where you are required to find this equation. We call it as a characteristic equation. Okay, so find the coefficients A4, A3, A2, A1, and A0. Okay, and then continue the fill up. Okay, using the determinant formula as I shown here. That symbol is a determinant. Okay, guys, it's not modulus. And that one, for example, A4, A3, A2, A1, okay, will give you A4 cross multiply minus A2, okay. So find the product of the cross multiply, and that will be the B1, okay, B1, then B2, then C1, then B1. And as you know that Ruth-Lewis have two special case, 0 in the first column and 0, the entire row is 0. So when you have a 0 in the first column, first you have to replace that 0 with epsilon. Okay, over here, epsilon. So epsilon is a positive and negative number, a simple positive and negative number. Let's choose epsilon as 1. Okay, then you put -1 and +1 inside the table, and you see what is the sign change. For example, in this column, positive, positive, no change, positive, positive, no change, suddenly positive, negative. So meaning that we have a one sign change, then negative to positive is the second sign change, then positive to positive, no sign change. So meaning that we have two sign change. So when we have two sign change, meaning that we have a two poles, okay, on the right plane. And then for the zeros, when you fill up this Ruth-Lewis, you will find that at this stage of S3, for this example, all row are 0. So what we do is we find the equation of S power of 4. We create a auxiliary equation, and then we differentiate. Okay, and the new differentiation coefficient will replace the 0, which is 4, 12, and 0. Okay, and then we continue the fill up until the end. Just remind that you can refer to your previous books or previous notes on that particular theory. And then in order to do that, we look at this example. Okay, this example required to analyze this model, which is the open loop transfer function with unity feedback. Okay, you are required to find the frequency and gain K, omega, and gain K at root locus intersection with omega, G omega axis. Okay, so we start by analyze this one. We have what do you call that? Find the closed loop transfer function, which is TS. TS actually is from the GS. So this one is the whole thing is GS. Okay, in the box. So TS is closed loop. So GS 1 plus GS. Okay. So you will get this transfer function, closed loop transfer function. And at the bottom of the denominator is the characteristic equation. So this characteristic equation is equal to 0. And take the coefficients 1, 7, 14, 8 plus K, and 3K insert inside the root width as shown here for S4, S3, and so on. And of course, the last one will be 0. Okay. Then continue the fill up using the formula that's shown in the previous slide. The theory said that for root width, the first column, this is the first column, must greater than 0 for stability. So 1 greater than 0, plus, okay. 7 greater than 0, okay. But this 3, 90 minus k square and 21k, we need to simplify. Okay, we need to simplify using the equation. K 90 minus k greater than 0 minus k greater than minus 90, k less than 90. This is the equation number 1. For equation number 2 is k minus k square minus 65k plus 7 to 0 greater than 0, which is 90 minus k. Okay, so I simplified minus k square minus 65k plus 7 to 0 greater than 0. Simplify again. K square 65k minus 7 to 0 greater than 0. So we have to find the roots for this. Okay. What is the roots for the k? Okay. What is the roots for the k? So in order to find the roots, we use calculator, or we just simply use the MATLAB at double prompt. We type here, k is equal to 165 minus 7 to 0 is the row vector. And then we use the command roots k. So roots k will give you two values, minus 74.64. And the other one is positive 9.64. Okay, so we ignore this one, we choose this one, the positive number. Okay, and that is the range for the maximum range. And the remaining one is 21k. Okay. 21k greater than 0, k greater than 0. So equation number 3. This one is equation number 2. Okay. So therefore, we get this range 0, less than k, less than 9.65. Okay. So that is the range for stability. So, you already know that 9.65 is the gain at the here, at the intersections, okay? Intersection, root locus, intersection with the d omega. Okay, so we use the even polynomial. Even polynomial we get from the root width, which is at s square. Even polynomial at s square, row s square row here. Okay, s square. Okay, so 90 minus k s square, 21k is equal to 80.35 s square, 22.7. So you find the s square, the s value, which is a plus minus j 1.59. So this one is equal to j omega. So therefore, omega is equal to 1.59 radian per second. Okay. So when we have this stability range, the most important thing is, do you understand this range? Okay. Do you understand this range? Yeah, I do. No, I don't. Okay. Okay. So when K is equals to 5, Khalid. Khalid. Okay.
Yes, doctor.
When K is equal to 5, what is the stability status? Stable? Stable?
Wait. When k equal to 5,
Yeah,
yeah, it is stable.
stable. Khalid, again, when K is equal to 10, is it stable or unstable?
No, it is unstable.
Unstable. Khalid, again, K is equal to 9.65. Is it stable or unstable?
It is unstable also, doctor.
Unstable.
Yes.
I'm afraid your answer is wrong, Aki. So,
Why?
K
Because
equal to 9.65 is critical.
critical. Okay.
Okay. As I
Okay.
mentioned here just now, when the intersection between the root locus and the imaginary axis. So you must understand the three situations. When K equal to 5 is stable, when K is equal to 10 unstable, and K 9.65 is critical. Okay. And when student sometimes getting confused, okay, this one is a critical stable. This one, guys, is critical dam. This is two different things. Student always said it the same. Okay, so actually it's not the same. Critical dam is when the zeta is equal to 1. Critical stable is when the zeta is equal to 0. Okay, at imaginary axis, zeta equal to 0. At this quadrant, zeta is between 0 and 1. At this in real axis, zeta equal to 1. And how about here? The unstable region is zeta is less than 0, which is negative damping. Okay. I repeat, saya ulang. At the real axis here, damping, zeta equal to 1, critical damp. At this quadrant is underdamped. At imaginary axis is undamped. And on the right-hand side is a negative damp. That is the definition of damping. But in terms of stability, okay, stability, this region is stable, this region unstable, and on the top of imaginary axis is a critical stable. I hope you understand what I said just now. Okay, guys? Are you okay? Hello?
Okay.
Yes,
Okay, wow, man.
understand.
Mantap. So, teruskan, we continue. Again, this is the simulations. Okay, to verify our answer. Just now that K critical is 9.65 by calculation. By simulation, Alhamdulillah, is the same. And the pulse value is 1.59, which give you 1.59 radian per second. This omega is also known as oscillation frequency, because when the root locus intersect with the imaginary axis, it is critical stable, and the response is like this. Okay, is a oscillation. Okay, time versus output. But for the on the negative part, okay, when zeta is a negative damp, so the response will be dangerous. Okay, is bigger when times towards infinity. So this kind of response is unstable. And unstable will give you unsecure or not safe condition, which will cause accident to the human. Okay, if the system is unstable, so it's unsecure. So when unsecure, you cannot control and it will cause you accident. For example, when you go for take a flight, maybe the system is not stable, so it will go hit the ground, okay, and everybody died due to the unstable conditions, which response is the red color. Okay. So far, okay?
Yes.
Any question?
No question.
Right. So the rule number 8 is the departure angle and arrival angle. So angle of departure is theta D. Angle of arrival is theta E. This angle can be calculated, okay, to further refine and enhance our sketch. So it use complex open loop poles and open loop zeros. The root locus depart from the complex open loop poles and arrive at complex open loop zeros. So when arrive, we call it as theta E. This one is referred to complex conjugate zero. But for the depart is reflect to theta D. Theta D is correspond to complex conjugate poles. So please remember this. Theta departure is on the complex conjugate poles. Theta arrival is on the complex conjugate zeros. And they have their own formula, which shown here. Theta arrival is summation of angle of all poles to B minus angle of all zeros to B plus 180. So similar to theta D as well. And E and B is referred to this point. Okay, E and B, right? The next figure on the notes. So you can see here, we have about 6 angle. Okay, theta 1 until theta 6. So we go for the angle of departure first. Okay, angle of departure, dia must use complex conjugate poles. So in this case, the complex conjugate poles is here. Okay. For theta arrival, must use complex conjugate zeros, which is here. Okay, guys. So we have 6 angle. Okay, our area of concern is the theta 1 angle of departure. Okay, is it theta 1? Yeah, yeah, yeah. Theta 1, theta 2, theta 3, theta 4, theta 5, theta 6. Theta 1 is because of the poles. Theta 2 poles as well. Theta 2 is 0. Theta 3 is referred to 0 as well. Theta 4 is reflect to the poles. Theta 5 is poles. Theta 6 is zeros. Equal to 2k plus 1, 180 degrees. So similar to the theta arrival as well. So we use this example to realize how this angle of departure applied in the problem shown here. So you have a open loop transfer function here, unity feedback, okay, which give you open loop zeros 1, which is -2. So open loop poles is 1, 2, 3, 3, and the value is -3, -1 plus J1, -1 minus J1. Okay? When you factorize this, S squared plus 2S plus 2. Okay, guys, you plot. Okay, and this is the given plot. Okay, this is -1 plus J1, and this is the zeros. Okay, at -2, and this is the poles at -3. Okay, -1 plus minus J1. So we have three root locus paths because we have three open loop poles. Okay, so this is root locus path number 1, number 2, and number 3. Okay, infinity, infinity, and this one ended at zeros. All right. So we measure the theta departure angle, which is here. Our area of concern is theta 1. So if you look at theta 1 is angle of departure is a positive. Okay, it's more than 90 degrees, but exactly we don't know. Okay, so we have to calculate. So we use the formula as shown in the red color in the previous slide. Okay, and then we start measure theta 1. Okay, so theta 2 is here, is 90 degrees. Okay,
خبزتين
let's
ليه
see
خبزتين
off your mic.
لا خبزة
Right, so 90 degrees, so theta 1, theta 2, where is theta 2? Theta 2 is here, sorry, 90 degrees, theta 1 under concern, theta 3, that is theta 3. So theta 3 is a triangular, okay? Using the trigonometry, how we find theta 3, the angle? Yasir? Yasir? Okay.
Theta 3, it will be tan 1,
Mm-hmm.
tan 1 over 1. Yes.
Kam هذا؟ berapa?
Was 3. 45.
Shukran Habibi. And Yasir again, theta 4.
This will be tan 1 over 2.
Mm-hmm.
26.5.
Shukran Habibi. 26. Okay. So we insert inside here. Insert inside here. 90 degrees, theta 1, and then we will get the value is about 108. Theta 1 is 108 degrees. Okay, so that is your theta departure. Okay. Why there is no theta arrival in this case? Miss Lee, where is theta arrival in this case?
Theta arrival is at infinity because right now we have 3 poles, but we only have 1 0. So it should arrive to pole, and then our poles will be at infinity. So that's why didn't have the angle.
Your answer is too long, Miss Lee. I'm afraid your answer is wrong. Theta A is not available due to no
Infinity.
complex conjugate zeros. There is no complex conjugate zeros in this case. Meow. Complex conjugate zeros started. Okay. So that's why theta arrival is not available. Right, we go to the rule number 9, plotting and calibrating the root locus. So all points on the root locus satisfy the magnitude and angle properties so that we can assume it is close to poles. So we want to locate points on the rule locus and their gain. For example, when the rule locus is crossed the line representing 20% overshoot, what is the gain over there? What is the closed loop pulse? What is the zeta value? Mr. Lim, what is the zeta value, Lim? Lim? Aiman? Oh, Aiman? Aiman dah datang. Yasir, okay? Yasir?
Doctor. Yes.
Overshoot 20%, what is the zeta value? Refer to the WhatsApp, the referred graph, the second graph.
Right. Second graph. Right, the zeta value.
Hmm. From the graph, the second
I'm not
graph.
sure, doctor.
You see your phone, there is two graphs.
Yeah, I'm seeing the graph.
You see the graph, you see on the y-axis 20% overshoot, and then you go to the right until it touch the curve.
It touched the curve and 0.9 damping ratio.
0.9.
9.
No, la 0.9. 0.20%. Use your ruler. 42, 44, 46, I think. After the 20% straight line touch the curve, go down.
It's 0.4123. Yeah, it's 0.46.
This one. Okay, this one. Okay.
Mm-hmm.
What is overshoot percentage? Has a zeta. And then 20% is over here. Okay.
Yes.
Right. And then
Correct.
go down there is 0.46. Okay. Clear? So this graph is
Here, yes.
important, guys. Very important, this graph. You don't have to remember the formula. Just see the graph. 5 seconds, you get the answer. Okay. So please do so. So I repeat again. Okay. So we have a pulse here. And we have a straight line. This is the origin, guys. So this one is zeta 0.46. And the angle here, you must know the angle. The angle is cos theta equal to zeta. Cos theta is equal to 0.46. So therefore, theta is equal to inverse cos 0.46, which will give you Tamimi?
62.61.
And 61 degrees. Okay? Okay, guys? Understand? Can
Yes, I understand.
Okay, good. And the gain K at that point will be K 1 over GSHS or 1 over the magnitude. You get the gain K value.
Doctor,
Yes.
it's 62.61,
Oh, yeah. 52.61. Shukran.
not 52, 62.
62. Oh,
Yes.
Tamimi, 62.
Yes, 62.
Right. So example 8, where you are given this open loop transfer function. Okay. So you need to sketch the root locus, find the gain K and intersection point, find the angle of departure, and verify it using MATLAB. Okay. So Open loop zeros, one value only. Yani -2. Open loop poles, 2. Help me to find the roots. Miss Lee?
Wait nè.
Oh, wait. Correct.
2 plus minus 3j.
J3. Okay, thank you. Appreciate. Okay, so we plot. Okay, so this is -2 minus J3. This is a -2 plus J3. And this one is yeah, -2. Okay. Okay. Okay, guys.
So,
Yes.
is positive
Yeah.
to
Yeah. Just testing.
negative.
Testing whether the student sleeping or not. Sorry.
Okay.
All right. Plus 2, Sorry, Right. So the question asks you to find the gain key and find the break-in point. Okay. This one. Okay. So what is the point of this? By looking here is about 4 point something or 5 point something. I'm not sure. And I think this one is from the computer is J 0.48. Okay. And the gain is 3.99 by simulation. And the break-in point, break away or break in? Break in. Okay. Break-in point is about -7 with the gain K with okay. Damping 1. Damping 1, Damping 1 meaning critical damp. Not critical stable. Fine. This one, this one, zeta is equal to 0. Undamp. But critical stable. That is the concept that you must understand. Okay. So we want to calculate this one and we want to calculate this one, the corresponding gain as well. Okay. So we use the Roos-Lewis criterion. Okay. So take this one equal to 0. Okay. Equal to 0. Now this one is the K minus 4. 1, 1, K minus 4, 2K plus 13, 0. Okay. And then continue. So 2K plus 13. So this one, first column, First column, this one greater than 0, okay. Then K minus 4. K minus 4 greater than 0, K greater than 4. First equation. And then 2K plus 13. 2K plus 13 greater than 0. 2K greater than minus 13, K minus 13 over 2. How much? 6.5, Correct. 6.5. So therefore, the key for stability for critical stable, okay, K is equal to 4. Okay, so use this K equal to 4, insert inside the even polynomial. This one is an even polynomial. Okay. Inside here. S squared plus 2k plus 13. K equal to 4 simplified. So square root 21 is 4.58, which is omega. Okay. So this point is plus J 4.58. Okay. And the break-in point is by using the calculus. Okay, UV, which is the V du U dV over V squared. Okay, so you get this. Simplified, this one cross multiply. Okay, so cross multiply, you will get this equation, quadratic. Factorize, you get -7 and 3. So 3 is not relevant. Okay, because from the plotting, from the freehand draw, the break-in point is at -7, which is over here. Okay, guys, -7. And how to calculate the gain on the break-in point? You can use Pythagoras theorem. Okay, for example, in this case, L1 the length here is 3, and the baseline is 2, 9. Okay, so L1 is square root 9 square plus 3 square, which is equal to 9.48. Okay, so same to L3 as well, 9.48, while L2, the length is about 2 minus 7, 5. Okay, so you get use this formula for length. K is equal to 18. Or you use this kind of formula, which is S square minus 4S plus 13, the poles, divide by S plus 2, modulus. Then replace S is equal to minus 7 inside this K value. I think this one is much better compared to the theorem Pythagoras, and you will get the same answer, which is K is equal to 18. Okay, 18. Lim, 18. Correct. Lim? Lim tidur.
So it's counting. Counting.
K is equal to 18. Then the next one is the angle of departure. Again, this one is using a formula. So the correspondent point is here, over here. Okay. So just use the formula. Okay. This one is 90 degrees. Okay. And -2 here, you have to use this point. This one is 3. This one is 4. Okay. The angle is say theta. Theta is arctangent 3/4. Okay. And then find the remaining here. So it is minus 233.1 by using the formula.
So
Yes.
for this page 81, right?
Mm-hmm.
I don't understand because in the red noted the formula is actually theta of the variable equals to angle of all zeros to A minus angles of all poles to A plus 180, right? But when going down, this one, the explanation, how is it same with the rate formula there? The solution formula and the rate formula. Yeah, and the tangent inverse of 3/4, that formula.
Right.
Why I can't see to relate these two? Is it using the
This
rate
formula you
formula?
understand? You understand this?
Yeah,
Okay.
the red color one understand, but I
Ah,
cannot
so-
understand why the solution same as the red one.
Okay, this one is the angle of what? Angle of zero.
This one
Zeros
angle
minus 2, am I
of
right?
0. Yeah.
Zeros minus 2 over here. Is a triangular.
Uh-huh.
Is a triangular. This one is
Uh-huh.
minus 2, this one is 2. So the length is 4. The
E
height is
I
3.
mean is I mean is now the solution given is actually the sum of angles of 0 to A
Okay.
and then minus sum of angles of poles
Okay.
to A
Okay.
equals to 180. Yeah.
Plus equal to 180.
Yeah,
If not
but
equal to 180, so you
yeah, but
cannot find it.
how is it relate to the rate noted one formula? Because according to that one, then we should angle of D equals to. So these three, so the angle of D, the theta should be left hand side, right?
Yeah.
And then equals to tangent reverse of 3/4
Which is this one.
minus 90 degree plus 180, right?
Which is the
If
minus 90.
according to red color formula.
Yes. So the answer is minus 233.1. Is about I think this one you have to minus with 360 minus 233.1. Then you get this particular value. What is the difference between 360 minus 233? 360 minus 33.
You mean what's the value?
The value. Subtraction.
127.
127. It's more than it's somewhere here.
Yeah, but the point is, okay, for the black colored solution, I can't see how to relate with the red noted formula. Because if let's say like this, then my angle of the angle of departure, okay, it's the unknown theta, right? So I thought it should be theta equals to tangent inverse of 3/4 minus 90 degree plus 180.
Theta
So
equal
if
to
we move here and there, then by right should be theta equals to tangent inverse 3/4 minus 90 plus 80 plus 180. Yeah.
Yeah, you bring this one, okay, and you bring this one to here.
But if you bring the right side 180 to the left side, then become minus 180 already. It's not same with the red color formula, right?
Yeah.
Because red color is plus 180.
Yeah, I manipulate this equation. Let me explain in the next class face to face on this methods. Okay,
Okay.
slide 81. But the previous one you understand. The previous one.
Previous one.
Previous one yang mana yang ini? Yang ini.
Previous one, this one I also cannot understand. How is it relate
Tak
between
nampak. Okay,
the red
tak nampak. Okay.
color formula with that one?
Okay, tak nampak tak apa. Nanti I explain again during the face to face.
Okay.
All right. So we stop here. Slide 83. Take note. Okay. So next 2 weeks we will go to this problem again. How to explain these two examples. Mungkin tak nampak the theta departure. Okay. Dia tadi baca due to the complex conjugate force. So, 83 we stop here. Time is running out. You have class next this, after this?
No,
Okay.
class cancelled.
Class cancel. Okay, thank you very much for the attention. I would like to take this opportunity to wish Selamat Hari Raya Aidilfitri to Arab brothers, Eid Mubarak, Minal Aidin wal Faizin, and for the non-Muslim is Happy Holidays. Next week, no class. The whole week, third week, no class. And we'll see you again on the fourth week on the 7th of April. Okay? Thank you very much. Bye-bye.
Thank you, doctor.
Thank you, sir.